Okay, quadratic residues. So this is lecture 4.5, quadratic residues. Okay, that's a lot of fun. So we choose some prime number p is prime, and then I can look at my z over pz. And I think of it as a ring, or a field if you want, field. So I don't not only add, I also multiply. So question, which elements in Z, let me say this is also, finite field, so Fp, in Fp are squares. So what is a square? I mean, it means that you have some element A in Fp, and then there exists x such that A is equal to x squared. Or you can think, if you want, that everything is integer and then A is congruent mod p to square of something. And let's look at some examples. So you can take, for instance, F3. And then if you take 0, z 0 square, 1 is 1 square, and 2 is not something square, because if you just square 0, 1, and 2, if you square 2, you will also get 1, so you will never get 2. And so 2 is not a square. So here 0 and 1 work and nothing else does. And you can take a F5, and now you see that it's kind of easier to just square up all elements and see what you get. So if you square up 1, you will get 1, if you square up 2, you will get 4, if you square up 3, you will get 9, which is again 4, and you square up 4, you get 1, and so 1 and 4 are squares, and 3 and 5 are not. And I will just include 0. 0 is always a square. So let's say non-zero. Okay, so in this way, we can take the whole Fp and we can divide it into two groups. So elements which are squares are called quadratic residues. Quadratic residues, mod p. And those which are not squares, so not squares, are called quadratic non-residues. So that's a definition. And also there is a fancy notation for it. So firstly, maybe so 0 is always here. Let me kind of give another example. So if I take F7, for instance, then again I can look at all squares. So what is a square? So 0 is definitely a square, 1 squared is 1, so it's here, 2 squared is 4, so 4 is here, 3 squared is 9, so it's 2 is here. 4 squared is 16 modulo 7 is 2, it's already here. 5 squared is 25 mod 7, it's 4, it's already here. 6 squared is 36 modulo 7, it's 2, it's already here. So basically all elements here are 0, 1, 4, 2, and so remaining non-residues are 3, 5, and 6. And so what it means that if you are trying to find some number so that x squared minus 5 is divisible by 7, you will fail. So that never happens. X squared minus 5 is never divisible by 7, because otherwise 5 would be a quadratic residue. So that's what's called a quadratic residue, and there is a fancy notation. So fancy notation is called Legendre symbol. And what it is, so this is just a symbol, and you write in brackets AP, and this is just symbol in brackets, and it equals to 1, 0, or minus 1. So 0 if P divides A, 1 if A is a quadratic residue and A is not 0, obviously. Sorry, in FP, I mean, doesn't divide, P is not doesn't divide A, and minus 1 is if A is not non-residue, quadratic non-residue. So that's the definition. Okay, you might ask why you want to do that. So, but you will see. So there are a bunch of questions. So first question, how many residues, how many non-residues are there? Second question, what are their nice properties? And third question is how to compute them. So let's start with just finding their number. Okay, so number of residues, of quadratic residues. So that's easy. So how we actually do that? So even in this example, we just took squares of all elements and that was it, right? So let's take FP and let's just take all squares of all elements, 0 squared, 1 squared, and so on, P minus 1 squared. So the question is how many different elements are there? So number of quadratic residues is just, cardinality of, let me denote the set by Q. And that's a set, so cardinality of Q. And by that I mean that I don't count things twice if they appear twice there but are equal to each other. And how to find the cardinality of this set? Okay, let's just check when two elements are equal. So suppose you have A squared is equal to B squared. That of course happens, so this happens if and only if A squared minus B squared is divisible by P, which happens if and only if A minus B is divisible by P or A plus B is divisible by P, which happens if and only if either the class of A equals the class of B or the class of A equals minus class of B. So basically what it means is that, so for two elements here to coincide, either they should be the same like before squaring, which doesn't happen, or this can happen. And this of course happens a lot because you have 1 and P minus 1 is equal to minus 1 each other mod P. 1 second. Okay, so so what it means? It means that if you just take all elements up to P minus 1 over 2, all of them will be distinct. So that means that if you take 0 classes, I mean, let's say class of 0, 1 square, and so on, P minus 1 over 2 square, so these are distinct. Because then you start to see, if you have anything else, for instance, if you take P plus 1 over 2, that's of course minus P minus 1 over 2 and modulo P. And that continues. So basically you have all numbers and then minus these numbers going in the opposite direction. So that's why actually the number of elements here is the cardinality of Q is just P plus 1 over 2. So this is number of quadratic residues, and these are residues. And then, of course, P minus P plus 1 over 2 will be non-residues. So non-residues are slightly less than residues, and the reason is, of course, there is this 1. So if you look at Legendre symbols, then you see that 1 appears P minus 1 over 2 times, minus 1 appears P minus 1 over 2 times, and this one appears, guess how many? Once. So that's the counting, and you see we have exactly that, 0, 1, 4, 2, 3, 5, 6. Okay, so then there is a beautiful theorem saying that if you take two residues and you multiply them, you get a quadratic residue. If you have residue, non-residue, you multiply them, you get non-residue. You have non-residue, non-residue, you multiply them, you get residue. And let's prove that now. So, little fact is that so let me say it using Legendre symbol. So it says that ABP is equal to APBP. So what it tells you, so if one of them is 0, then one side is 0, then other side is 0, and otherwise it tells you that if you have a quadratic residue and you multiply by quadratic residue, you get quadratic residue. If you take non-residue, multiply by non-residue, you get residue. So because you multiply -1 times -1 is 1, and then non-residue times residue is residue. And of course, different order. So this is what I want to prove, and that's pretty remarkable. So again, let's look at 7. So if you take this F7, then you have, you know, let's exclude 0. Then we have 1, 2, and 4 here, and 3, 5, 6 here, and then we can check. So 2 squared is 4, 4 times 2 is 8, mod 7 is 1, 4 squared is 16, mod 7 is 2. Okay, if you multiply any two residues, you get residue. That holds. If you multiply any non-residues, like 3 times 5 is 15, it's 1, we get here. 3 times 6 is 18, it's 18 is 2, we get here. 6 times 5 is 30, modulo 7 is 2, we get here. And this is non-residue times non-residue is residue. And if you start multiplying 2 times 3, you get 6. 4 times 5, you get 20, mod 7 is 6. So when you multiply two things in different halves, you get element here. And obviously you see there is some group homomorphism here, and so probably there should be some group theory involved. So let me derive that from things in group theory we know. So let's take a group. So firstly, which group we take? We take this multiplicative group of a field, Fp times, and another notation for it is Z over Pz times. That's a remainders modulo P thought as multiplicative group. It has P minus 1 over 2 elements. Sorry, P minus 1 elements. I'm sorry. So, perfect. And then, let's look at who are residues. So first, there is a homomorphism, which takes Z over Pz times and sends it to Z over Pz times. And what it does, it just takes every element and squares it up. So you should be careful. Squaring up is a bad homomorphism. It's not a homomorphism in general, but for a billion groups it is. And you can take any element and square it up. So let me call it F. So it's clearly a homomorphism, and we know that image of F is just squares. Everything which is square of something. That's set of residues. And if you want to find the number of it, we did it in some counting way, but you can also look at the kernel of F. And the kernel of F is clearly elements which go to 1. So these are x in Z over Pz times, such that x squared is 1. But you know, I mean, we are working in a field, so after all, you can say that this means x minus 1 times x plus 1 is 0 in Fp, which means x equal to 1 or x equal to minus 1. So there are two elements in the kernel which are just plus minus 1 mod p. And so cardinality of a kernel of f is 2. So kernel of f and kernel is just two elements. 1 and I can say p minus 1 if you wish. Minus 1 modulo p. But then I know that cardinality of the image by the factor group theorem, the first isomorphism theorem, is just you divide the order of the group, z over pz, times, and you divide it by the size of the kernel, and you get p minus 1 over 2. Okay, at least so far we just recovered that the number of quadratic residues is p minus 1 over 2, and that's of course the image. And then the number of non-residues is the rest, and if you add 0, which we kind of excluded when we looked at the group, you will get p plus 1 over 2. But that doesn't prove the fact. So the fact tells me something about Legendre symbol and that it is a homomorphism. So let's see that. Okay, so let's denote this image somehow. So image of f, I can denote it by, let's say, H. And that's a subgroup inside my group Z over PZ times. So that's a subgroup, and okay, I know that it is normal because I'm working with abelian groups. There is no issue here. And then I can look at a factor group. So Z over PZ times. There is this map, surjective map, to this factor group, and factor group is Z over PZ times divided by H. So what is this group, this quotient group? So this is a group which has two elements, right? Because we know that this H has order p minus 1 over 2. So this has order p minus 1 over 2. This has order p minus 1. When you take quotient, then you get that this has order 2. So this is a group of order 2. And I can say that it has two elements, let's say plus 1, minus 1. And operation is multiplication. And so what I got is a homomorphism to a subgroup of order 2, which sends some elements to 1, some elements to minus 1. And clearly, if you think about it, so elements which go to plus 1, so this is kind of neutral element, identity, right, in this group. So these are, of course, quadratic residues. And the reason is because they are in H. And elements which go to minus 1 is the only coset. And this is just quadratic non-residues. But of course, that just means that my homomorphism, let me denote it by P. So P of X is just Legendre symbol, X, P. And that's by definition. Legendre symbol is plus or minus 1, depending it's residue or non-residue, and 0 if you are equal to 0. So that doesn't happen when we work in Z over PZ cross. So that's why this means that this pi of x, this Legendre symbol, is a homomorphism. And you know, the fact that quadratic residue times residues, residue, non-residue times non-residues, residue, blah, 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 that is just the operation in the factor group, right? So it just tells you you have two cosets, you multiply them, and then you have the multiplication table of the group Z over 2Z. Okay, so that's what's the multiplicativity of Legendre symbol. And that's a beautiful property. And the next question, which is maybe the most interesting one, is how to compute these residues. how to understand whether some number is quadratic residue modulo some other number. And that can be pretty hard, because imagine you have something like, 1728 or 317, and the question is just, how would you go about computing that? That's not obvious. And there is a recipe, and the recipe is very easy to imply. Of course, if on top you have a number which is a product, you can use this, but what to do with this big prime underneath? And the recipe actually uses a marvelous theorem, which is one of the most beautiful theorems in mathematics, for sure, which is called quadratic reciprocity law. So let me formulate it and then explain how to use it to find residues and not residues.